Hello, I'm Christian Deppe. I am a researcher at the Technical University of Munich at the Institute of Communication Engineering. Today, I'm delighted to present you the work Computability of the Zero Error Capacity of Noisy Channels. This is a joint work with Holger Boche from the Technical University of Munich. I will start with a description of the discrete membrane channel, followed by a discussion about the Shannon capacity and Shannon zero error capacity. Then I continue with the question why we should use the zero error capacity. Then I will present you Shannon's approach how to calculate the zero error capacity. Another approach is due to Alswede, who uses some other channel model to calculate the zero error capacity. Then I will start with our investigation, how to compute the zero error capacity of a channel. Therefore, I present you the Turing machine and give you definitions of computability. Then I will present you our results on the algorithmic computability of the zero error capacity. Finally, I will give you some conclusions. Let's start with the discrete membrane channel, which you should all know. This was introduced by Shannon in 1948. Here, Alice has to transmit a message to Bob. And Alice uses a block code and an encoding function E to map the messages to a symbol of length n. The channel is modeled by a stochastic matrix. The probability for a sequence Y to be received if xn is sent is described by this matrix here. If Bob receives a word yn and uses the decoding function d, he can find out what was Alice's message. In 1948, Shannon defined the Shannon capacity. He defined that a rate is said to be achievable if there exists a sequence of codes such that the probability of error tends to 0 if the block length n tends to infinity. This is called the Shannon transmission capacity. In 1956, Shannon defined also the zero error capacity. Here he said a rate is said to be achievable if there exists a sequence of codes with probability of error equal 0 for all block lengths n. And the goal in both cases is to determine the channel capacity. So we have the Shannon transmission capacity, that is somehow the vanishing error capacity C, and we have the zero error capacity. This we denote by C0. Shannon by himself showed the relationship between the zero error capacity of a discrete membrane channel and the so-called Shannon capacity of a graph. He used graph theory to compute the Shannon capacity for a graph GW, which is usually determined from a discrete membrane channel W and referred to as a confusability graph of the channel W. The problem is that in the most practical applications, the description of a channel is available in terms of a DMC rather than a confusability graph, which seem to be often overlooked in information theoretic considerations regarding the zero error capacity. We believe that it is beneficial to investigate the problem of computing the zero error capacity as a function of the discrete membrane channel. It plays a central role in state estimation of unstable plans. This is shown by Matveyev and Zavkin in this paper here. Furthermore, we show how we can use the result of this presentation for control in this work here. Shannon also asked the question whether the zero error capacity of a discrete membrane channel can be linked to another error capacity of a suitable channel. Such an interesting connection was shown by Alswede. He showed that the zero error capacity of a discrete memory channel is equal to the maximum error capacity of a corresponding 0-1 arbitrary varying channel. The problem is that Alsvede's approach had not helped to calculate the zero error capacity or to provide specific properties until now. In particular, it's still not clear how Alsvede's result should help to compute the zero error capacity of a given discrete memory channel, since there is no general formula for the capacity of an arbitrary varying channel for the maximum decoding errors. Let's start with our investigation. We examine the question of the algorithmic computability of the zero error capacity of discrete memory channels and also the general algorithmic applicability of Chen's and Alsvede's results. As a model of computability, we employ the theory of Turing machines and Turing computability, which is suitable in order to characterize the capabilities of the real-world digital computers. What is a Turing machine? A Turing machine is a mathematical model of an abstract machine that can manipulate symbols on a stripe of tapes according to certain given rules. The Turing machine can simulate any given algorithm and therewith provide a simple but very powerful model of computation. So there's no limitation on the computational complexity. Furthermore, unlimited computing capacity and storage are assumed. And we assume that the Turing machine works completely error-free, and the most powerful programming language are Turing complete, such as C, C++, Java, Python, etc. All discrete computing models are equivalent. They are models of von Neumann, Gödel, and Minsky. And any arbitrary large finite dimensional problem can be exactly solved without errors by a Turing machine. Turing machines are suitable to study the limitations in performance of digital computers, because anything that is not Turing computable cannot be computed on a real digital computer, regardless how powerful it may be. Alan Turing introduced this concept of a computable real number in 1936 and demonstrated some principal limitations of computability. So in 1949, a computable monotonically increasing sequence which converges to a real non-computable number was constructed by Specker. So Turing defined a computable real number as a number for which there is a Turing machine which, given n on its initial tape, terminates the nth digit of that number encoded on its tapes. And we denote the set of computable real numbers by RC. We call a function Banach-Mazur computable if f maps any given computable sequence xn of real numbers into a computable sequence f of xn of real numbers. The second definition from Turing, we call a function Borel-Turing computable if there is an algorithm that transforms each given computable sequence of a computable real x into a corresponding representation for f of x. So this definition is equivalent to the original definition of Turing. The definition 1 of Banach-Mazur computability is the weakest form of computability. Now let's come to our algorithmic approach. We want to investigate the algorithmic computability of the zero error capacity of DMCs, as there has been no known closed formula for this function until now. So we consider whether the zero error capacity as a function of the channel is computable. And the first theorem gives us a negative result, because if we have two alphabets x and y of size greater or equal to, then the function of the zero error capacity is not Banach-Mazur computable. To show the theorem, we will give an example of a binary channel such that the zero error capacity is not Banach-Mazur computable. So we choose a delta greater or equal 0 and smaller than 1/2. And we choose a channel W delta as follows. If x is equal 1, then y is equal 0 with probability 1 minus delta, and y is equal 1 with probability delta. If x is equal 0, then y is equal 0 with probability delta, and y is equal 1 with probability 1 minus delta. If we now look at the zero error capacity, then of course it's equal 1 if delta is equal 0, and it's 0 if delta is between 0 and 1/2. If we now consider the function theta from 0 to 1/2 into 0 and 1, such that theta of delta is equal to the zero capacity of the channel W delta, then it's immediately clear that this function is not Banach-Mazur computable, and therefore also the zero error capacity function is not Banach-Mazur computable. Next, we look at semi-decidable sets. A subset of the computable real numbers is called semi-decidable if there is a Turing machine that stops for the input x if and only if x is a member of M. Otherwise, it can run forever. Now we want to look at the set of channels such that its zero error capacity is greater than lambda, where lambda is chosen between 0 and log2 min of x and y. And we showed that for every alphabet greater or equal to, this set are not semi-decidable. Now let W be a channel and N be a block length. Then by M star of W and N, we denote the cardinality of a maximum code with decoding error 0. Now we look at this M star as a function of the channel and want to know if this is Banach-Mazur computable. Our theorem says if the alphabets have cardinality bigger than 2, bigger or equal to, then M star is not Banach-Mazur computable as a function of the channel. The proof is very similar to the previous proof. So let x and y be alphabets of cardinality greater or equal to, and n be a natural number. Then we consider the ideal channel W1 such that M star of W and n is the minimum of the cardinality x and y to the n. And we consider the channel W2, which is a channel for which all transmission probabilities are bigger 0 for all y and x. Of course, M star of W2 and n is equal 1, and therefore its zero error capacity is equal 0. Whereas the zero error capacity of W1, of course, is positive. Therefore, we have a very similar situation as in the theorem 3. And therefore, we can use the same idea to show that the function M star as a function of the channel is not Banach-Mazur computable. We now want to examine the question of whether a computable sequence of Banach-Mazur computable lower bounds can be found for the zero error capacity. Therefore, we set f sub n of W equal to the maximum from 1 to n, this big N here, of these rates. And for all W and for all n, we know that Fn of W is smaller or equal than Fn plus 1 of W. And of course, we know that the limit of n to infinity gives the zero error capacity. However, this cannot be expressed algorithmically Because due to our previous theorem, we know that the functions Fn are not Banach-Mazur computable. We next want to show that this is the general phenomenon of the zero error capacity. So our next theorem says, again, we look at input and output alphabets of cardinality greater or equal to. And we show there exists no computable sequence of Banach-Mazur computable functions that simultaneously satisfy the following. For all n holds that Fn of W is smaller than the zero error capacity for all channels, and for all channels holds that the limit of Fn of W is equal to the zero error capacity. We made the following observation. For all computable real numbers mu greater or equal 1, the sets of graphs such that its channel capacity is bigger than mu are semi-decidable. Furthermore, it holds that 2 to the 0 error capacity is equal to the channel capacity of the corresponding graph to the channel. In the next theorem, we show that the following statements A, B, and C are equivalent. The sets of channels such that the zero error capacity is smaller than a given lambda are semi-decidable. The set of graphs such that the channel capacity of the graphs are smaller than mu for a given computable mu are semi-decidable. And finally, the sets of arbitrary ranked 0-1 channels such that its maximal capacity is smaller than a given computable lambda are semi-decidable. Finally, we look at useless channels in terms of the zero error capacity. This is a set of channels such that zero error capacity is 0. We showed that this set is semi-decidable. Let's summarize. Due to the importance of the zero error capacity, it is necessary to investigate its algorithmic computability, as there has been no known closed formula for the zero error capacity until now. We show that the zero error capacity of noisy channels is not Banach-Mazur computable and therefore not Borel-Turing computable. We also investigate the relationship between the zero error capacity of the discrete membrane channel, the channel capacity of graphs, and Alsweder's characterization of the zero error capacity of noisy channels with respect to the maximum error capacity of 0-1 arbitrary varying channels. We show that the important questions regarding semi-decidability are equivalent for all these three capacities. The Borel-Turing computability of the channel capacity of graphs is completely open. This is why the coupling with semi-decidability is interesting. The result from this work could be used to establish fundamental bounds on the capability of computer-aided designs and autonomous systems, assuming that they are based on real digital computers. Here are some references we used. So here in this work, Rudolf Alswede gives his characterization of Shen zero error capacity. This is our work where we use the result to show results in control theory. This is the work of Matveyev and Zavkin, who showed how important the zero error capacity is for control theory. And this is the work of Chen, where he introduced the zero error capacity. More references can be found in our article. Finally, I want to thank you for watching this video, and I also want to thank our sponsors who support us doing our research work. I hope the video helped you to understand our work. Questions can, of course, send to Holger Boche or me via email. I hope really that the next ITW in Bombay will take place again in presence.